2.34 watts. That is the measured output of a rose-shaped wind turbine at a wind speed of 9 meters per second, roughly a nightlight. And here is the strange part. It won. In a peer-reviewed paper published in March of 2025, that turbine was tested against two rival flower-shaped designs, and it beat both of them. The number is real. The comparison is real. The turbine genuinely won its category. So this video is not about whether the claim is true, because it is. It is about what happens when you ask what the claim was measured against, and about the one metric where vertical turbines genuinely do beat every conventional wind turbine on Earth, verified in a field study in the California desert. By the end, you will know exactly which is which. Let us dive in. Wind power is the only way of generating electricity where people care what the machine looks like. Think about how strange that is. Nobody has ever chosen a solar panel for its appearance. Nobody objects to a transformer on aesthetic grounds. Nobody drives out of their way to photograph a gas turbine, and no local newspaper has ever run a front page about the visual impact of a substation. But wind turbines are argued about visually. They are argued about in planning meetings, in letters to councils, in local referendums, and in national newspapers. People describe them as elegant or as blots on the landscape, and both camps are entirely serious. In a great many cases, the visual argument is not a side issue that follows the technical decision. It is the argument that decides the outcome. Now think about what that does to the market. If appearance can block a project, then appearance has commercial value. And if appearance has commercial value, there is a permanent, powerful pull toward turbines that look beautiful regardless of what they produce. So beauty and efficiency have been quietly at war in this field for 100 years. And beauty keeps winning the photograph while efficiency keeps winning the balance sheet. Which is why, every few months, an image of an elegant turbine circulates with an extraordinary number attached to it. A spiral, a tree, a flower. And the number is almost never given in units that can be compared to anything else. In every other corner of energy, a machine is judged by what comes out of it. In wind, it is judged by what it looks like from the road. Hold that thought, because the most beautiful wind turbine ever built is now a museum. A vertical turbine has one property that no horizontal turbine on Earth possesses, and it is not efficiency. It does not need to face the wind. That sounds minor until you consider what a conventional turbine has to do. It carries a yaw mechanism, motors, gears, and a controller whose entire job is to swing a nacelle weighing many tons around, to point at wherever the wind happens to be coming from at that moment. Every time the wind shifts, the machine has to chase it. A vertical turbine simply turns. Wind from the north, wind from the west, wind swirling in 3 directions at once around a building. The rotor does not care and never has to be told. That brings 2 more advantages with it. The generator sits at the bottom, close to the ground, where a person can actually reach it without a crane or a climb. And the blade tips travel more slowly, which makes the machine measurably quieter. Everything a vertical turbine is good at. It is good at because it gave up on being efficient first. So the obvious question is how much it gave up. There are 2 ways to build a vertical turbine, and both were invented within a decade of each other. The first came from Finland. In 1922, an engineer named Sigurd Savonius patented a rotor built from curved scoops arranged around a vertical shaft. It works exactly the way it looks like it works. The wind pushes against the concave face of one scoop harder than it pushes against the convex back of the other, and the difference turns the shaft. That makes it a drag device, and drag devices have 2 enormous virtues. They are mechanically simple, with almost nothing to go wrong, and they start themselves in nearly any breeze, without help. They are also genuinely inefficient. A Savonius rotor typically converts well under 20% of the energy available to it. The second design came from France. In 1931, Georges Darrier patented something quite different. Curved blades, shaped like aerofoils, sweeping around a vertical axis. This is a lift device. The blades do not get pushed. They generate lift, the same way an aircraft wing does, and that lift pulls them around the circle. The result is a machine that can spin several times faster than the wind blowing through it, and it is far more efficient than a Savonius. It also cannot start itself. A Darrius rotor sitting still produces no lift at all, which means it needs a motor, or a small Savonius bolted on. simply to get moving. Now, the problem neither of them solved. A vertical blade travels in a circle, which means that during part of every single revolution, that blade is moving against the oncoming wind rather than with it. It is not producing useful power at that moment. It is being dragged through the air. No blade profile removes that. It is geometry. So here is the ladder, and it is worth memorizing because everything else in this video sits on it. The absolute theoretical ceiling for any wind turbine is 59.3%. Large modern horizontal turbines achieve roughly 50. Credible small wind systems land somewhere near 35. And the Rose turbine we are about to examine measured a coefficient of power of 0.1 at low wind speed, 10%. That is not a scandal. That is simply what a small bio-inspired rotor does in slow air. In 1984, on the south shore of the St. Lawrence River in Quebec, Hydro-Quebec and the National Research Council of Canada began building the largest vertical axis wind turbine the world has ever seen. They called it Eole, after the Greek keeper of the winds. The scale is difficult to hold in your head. It stood 110 meters tall. Its rotor measured 64 meters across at the equator, sweeping 4,000 square meters of air. The rotating mass came to 880 tons, and the alternator alone weighed 100. And that alternator sat at ground level, not up in the sky in a nacelle, but at the bottom of the column, where it could be reached and serviced the vertical turbine's great structural advantage, a low center of gravity, made real at industrial scale. The blades were steel, not because anyone preferred steel, but because the composite materials that make modern turbine blades possible were not yet mature enough for a machine this size. It was rated at 3.8 megawatts, and it reached 3.4 in 1988. It went into service in 1987. Now, the part that gets left out when people call it a failure. Eole ran for 18,550 hours. It generated roughly 12 gigawatt hours of electricity, 12 million kilowatt hours, delivered to a real grid. This was not a stunt or a model. It was a working, multi-megawatt power plant, and for several years it was the largest wind turbine of any kind on the planet. Then, in 1993, the bearing at the bottom failed. That is the entire ending. Not aerodynamics, not efficiency, not the wind, and not the Darius principle. A single bearing at the base of an 880-ton rotating column, and repairing it was judged uneconomical. Eole was never dismantled. It still stands at CapChat today, and since 1994, it has been an interpretation center. There are guided tours through the summer. If you pay a little extra, they will take you up to the top platform, and the view across the Gaspé Peninsula is spectacular. It remains, by a wide margin, the largest vertical axis wind turbine ever constructed. It is also, by a wide margin, the most photographed. The machine that failed as a power plant succeeded as a landmark, which is the oldest story in this entire field. In 2010, a fluid dynamics professor at Caltech named John DeBerry was studying the swirls of water left behind by schooling fish. He noticed something that had no obvious business mattering to wind power. In a school, the vortices shed by the fish do not all rotate the same way. Some turn clockwise and some counterclockwise, and the fish arrange themselves so that a neighbor's turbulence helps them along instead of holding them back. Conventional wind farms do precisely the opposite. Every horizontal turbine leaves a wake behind it, a column of slowed, churning air that will rob any turbine standing in it. The industry's only answer to that problem has ever been distance. 3 or more rotor diameters between machines side by side, 5 to 10 in front and behind. In DeBerry's own words, a mile is not uncommon for downwind spacing, which means a wind farm is mostly empty land, and the emptiness is not waste. It is a requirement. With 2 graduate students, Robert Whittlesey and Sebastian Liska, DeBerry modeled what would happen if you arranged vertical turbines the way fish arrange themselves. That work was published in Bioinspiration and Biomimetics in 2010, and the model predicted an order of magnitude more energy from the same parcel of ground. So he bought 2 acres north of Los Angeles and built the field laboratory for optimized wind energy to find out. The array was 24 turbines, each 10 meters tall and 1.2 meters wide. spaced about 5 meters apart, close enough that a conventional wind farm would consider it absurd. And every turbine spun in the opposite direction to its neighbors. The measured result was 21 to 47 watts per square meter of land. A conventional wind farm produces 2 to 3. Now hold on to the detail that makes this remarkable rather than merely impressive. Achieving that required no improvement in individual turbine efficiency whatsoever. Not one. Every machine in that array was, on its own, a worse turbine than a conventional one. They won as a crowd. So where does a 3D printed flower fit into that? Exactly where its own authors put it, and nowhere else. The paper is real, and it is honest. In March of 2025, a team including Nugraha, Wiranata, and Muflikun published a comparison of 3 bio-inspired vertical turbines in the journal Results in Engineering. They designed a new rose-shaped rotor, additively manufactured it, simulated its behavior, and then tested it against 2 existing bio-inspired designs already on the market, the Eole and the Tulip. Here are the numbers they measured. At 3 wind speeds. At 3 meters per second, the rose turbine produced 0.12 watts. At 6, it produced 0.67. At 9 meters per second, a properly stiff breeze, it produced 2.34 watts. And their conclusion, in their own words, is that the generated power is the highest among the Tulip turbine and the Eole turbine. So the claim in the title of this video is true. The rose beat everything it was compared against. And what it was compared against was 2 other flower turbines. Now let us put 2.34 watts somewhere you can feel it. That is roughly a nightlight. A modern offshore wind turbine rated at 15 megawatts is about 6.4 million of them. And at a realistic capacity factor, 1 rose turbine produces something on the order of 2 kilowatt hours over an entire year, around a quarter of what a single LED bulb burns in the same period. I want to be very clear about where the fault lies here, because it is not with the researchers. Nobody lied. Nobody was hiding anything. A research team compared 3 flower turbines under controlled conditions, reported which one won, and published the whole thing openly. Somewhere downstream of that paper, the phrase, "more than all wind turbines," got attached to a result that never claimed it. But here is what makes this genuinely worth your time. There is a metric on which vertical turbines really do beat every conventional wind turbine on Earth. Dabiri measured it in the desert, watts per square meter of ground, where they win by a factor of 10. That claim is real, it is verified, and it has nothing whatsoever to do with the shape of any individual rotor. None of this makes a small vertical turbine pointless. It makes its purpose specific, and the purpose is usually not electricity. Look at where a device like this genuinely earns its place. The first is powering something small in a spot where a cable cannot reasonably go. A sensor, a sign, a light on a path, a weather station on a remote roof. In those cases, you are not competing with the grid. You are competing with a battery somebody has to climb up and replace. The second is teaching. A turbine a student can print, hold, and measure is worth more in a classroom than any diagram, and the paper we have been discussing is exactly that kind of work, a genuine, published, careful comparison of 3 designs, done properly. And the third is demonstration, where the visible fact of a spinning object is the actual product, a building that wants to show it cares, a public installation, a visitor center. In those cases, the electricity is not the point, and never was. And pretending otherwise is what causes the trouble. If you want to go deeper on this, we put together a full guide to assessing small wind the site survey, the metrics that actually matter, and the questions worth asking any vendor before you spend anything. The link is in the description below. Now the rule, and it is short. If what you are buying is watts, buy the least beautiful machine you can find on the tallest tower your permit will allow. Appearance costs money. Efficiency does not care what anything looks like. But if what you are actually buying is a quiet, safe, visible object that people will accept standing next to a building, then say so plainly. Price it as the sculpture it is, and treat whatever electricity it makes as change. One last thing, and it is about how to read the next one of these you see. Before anything else, check 3 things, whether the figure is given in watts or in watt hours, because those are not the same claim, whether it is peak output or annual production, and what it was compared against. A great many extraordinary numbers survive the first 2 questions, and dissolve completely at the third. A rose-shaped turbine produces watts, not kilowatts, and no amount of pedal geometry changes the order of magnitude. It will not run a house. It will not run a refrigerator. It will not boil a single kettle. Its coefficient of power is a fraction of what a conventional machine achieves, and that gap is not a manufacturing problem waiting for better materials. It is geometry. A vertical blade spends part of every revolution moving against the wind, and no design removes that. And the one genuine advantage, the one debris measured in the desert, only matters where land is the binding constraint. Land is very rarely the binding constraint. Cost usually is. But none of that is a verdict against the vertical turbine. It is a verdict about what job you are hiring it for. These machines lose as individuals and win as a crowd, and almost every disappointed buyer bought one expecting a champion. The largest vertical axis wind turbine ever built stopped generating electricity in 1993, and people still drive across a province to stand underneath it. That tells you something true about this technology, that no efficiency figure ever will. If discovering the practical, unglamorous corners of energy engineering matters to you, subscribing and sharing is the simplest way to make sure this kind of knowledge keeps being found. We will be tracking all of it as it develops. So here is the question. A beautiful turbine on your roof that makes a few watts and everybody asks about, or an ugly one on a mast at the bottom of the garden that makes 20 times more and nobody mentions? Which one are you actually buying? I would genuinely like to know. Drop it in the comments.